In this video, we'll look at the memory of the modern computers. If you recall from last time, we saw that in theory we have this very simple model of a computer. We have a processing unit and a memory, and reading or writing to memory takes constant amount of time. We saw that in some problem it's unrealistic to assume this. In particular, if the input is so big that it lies on the disk, then we cannot assume that we can read the disk in constant time. In this model, we assume that we need to read the disk in blocks. We can still assume constant access time to the memory, but the disk should be modeled using a different model that was the I/O model. However, modern computers are even more complicated than this. In particular, if you look at the picture of a modern computer, it might look something like this: that you have multiple cores, and these cores are connected to a special kind of memory called this shared L3 cache. So what is this caches? What are these caches and how do they behave? So the modern architecture of a computer looks like this. So you have multiple cores. Each core has specialized cache memory, L1 cache and L2 cache. They're all connected to a common L3 cache, which is in turn connected to the common memory, and they all can access the common disk. So what are the access times of these memories? So if you look at the latency, or how much time it takes for you to read one element from these memories, then the numbers look like this. So L1 cache is obviously fastest. L2 cache, we could say twice slower. L3 cache 2 or 3 times slower, and the memory is twice slower than the L3 cache. In particular, if you compare memory to the L1 cache, it could be a factor of 20 or 30 times slower than the L1 cache. And if you go all the way down, disk could be very, very slow. Could be a factor of a million slower than the top of this memory hierarchy. When you look at the size of these memories, you see that L1 cache is smallest. Then again, the size of these memories increases exponentially until you have terabytes of disk space. Since the memory at the top of this hierarchy is the fastest, you prefer the element that you want to use in your CPU to be at the top of the cache, at the top of the hierarchy. In particular, this means that if you read an element from the disk, and if you want to keep it in the memory as long as possible, if you put it in the L3 cache, you want to keep it there as long as possible. In particular, you want to keep the most frequently accessed memory locations in the L1 cache, because then you have fastest access to them. The way to do this is often through exploiting localities. So you can have two types of localities. If you read an element, then it is expected that you might read that element again in the recent future. Or if you read an element, it is expected that you might read the elements next to them again in the recent future. So this means if every time you read an element from the memory, it is put in the L1 cache together with some of its neighboring bytes of the memory, and it is kept there until it needs to be thrown away, and another memory element could be placed instead of it. So the idea of the cache should be clear by now. We would like to keep the most frequently used elements in the cache. So how do we do it? There are many different caching strategies. We now look at some of those. So one way to assign memory locations to cache is through direct mapping. In this way, every memory location can be stored in only one specific location in the cache. Assume we have a memory that has 16 memory cells, and we have a cache that can store up to 4 items from the memory. Direct mapping does something like this. You take the first element of memory and you map it to the first element of the cache, the second to the second, and all the way, and then you wrap around. So if you look at this picture, then you can see that this mapping is basically just uses the 2 least significant bits of the address to get to the corresponding address in the cache. For instance, if you have 1001, you take the first 2 bits, and 01 is the address of where this guy is mapped to. So this means if you read this memory cell, this is placed over here. If you read one more memory cell, then if you see this memory cell, then it's placed here. If you want to read this memory cell again, if it's in the cache, then we don't need to go to the memory to fetch it. Okay. So what are the advantages and disadvantages of this approach? The main advantage is that this is very simple to implement into the hardware, and in fact, it's also a valid caching strategy. The main disadvantage is that it's not very beneficial compared to the other caching strategies. For instance, if I am using these two memory cells, 0000 and 1000, and if these are the only two memory cells that I'm frequently accessing, they both cannot be in the cache. Because once I access this memory cell, the next time I access this memory cell, I have to throw away the old contents of this cell, which means the next time I'm accessing 000, it's not in the cache. So I'm essentially, if I repeatedly access these two memory cells, I'm gaining no benefit from this caching strategy. The other caching strategy is fully associative. In this way, in this method, there is no fixed location for a memory. A memory cell could be any of the positions in the cache. The main advantage of this strategy is that this is the most efficient caching strategy available, since it does not put any restriction where we can put an element. The main disadvantage is that it's very difficult to implement in the hardware, especially because we have to have a lot of bookkeeping information to figure out, to find the elements in the cache, since they could be anywhere. In the previous method, there was only one possible location that you need to look if you wanted to find an element. In this method, you need to look at all possible locations to find an element. An approach that tries to strike a balance between two approaches is the k-way associative way. This picture shows a two-way associative cache. In this method, a memory location has two possible locations, as opposed to one or all of the cache. So we take the first memory element, we have the two possible locations that are the first two locations of the cache. The second is mapped to the second two, and then we wrap around again. So the third element has the first two possible location as its possible location in the cache, and so on. As I discussed, this is the compromise. It gives us more cache performance compared to direct mapping, and it's also harder to implement, easier to implement.